So here's a dynamics example that involves two blocks that are connected over a pulley by a rope. And in fact, the system is released from rest, and the question is, how long does it take the box to hit the ground? So that sounds like a kinematics question, right? How long? And if this system releases from rest, I expect that 8 kilogram block to accelerate downward, right? And this 1.5 meters is like a delta y, and the question is looking for a delta t. Right? That's a kinematics question. The issue, though, is this acceleration. So this block is not going to fall in free fall, right? This is not free fall. The 8 kilogram block has gravity pulling down, but it also has tension pulling upward. And that's going to slow the block down. So it will accelerate downward, but it's not going to accelerate at 9.8 meters per second squared. So how fast is it going to accelerate downward? Well, to answer that question, I have to answer a dynamics question, right? Meaning I need to apply Newton's second law to both of these objects and decide what the acceleration of the system is. So let's sketch that out very quickly. So the question is, find delta t, right? Which again is kinematics. But to do that, I need to find the acceleration of the system, which is going to come from dynamics. Okay, so again, what I really want to know, let's call these blocks, let's label them. Box 2 and box 1. And there. What I really care about is the acceleration of block 2, right? I mean, what I really care about is delta t. But the acceleration of block 2 is going to help me solve the kinematics question. So finding A2 here is critical. Again, block 2 has weight acting downward on it and tension acting upward on it, and that tension is transferred around this pulley into this 5 kilogram block, which also has weight acting on it. So to find that tension, I'm going to need to draw a free body diagram for both of these objects. All right, and I think that'll become clear once we actually do that. So let's do that. So let's draw a free body diagram 1 for block 1. So I'll draw our vertical line and my ruler line, my horizontal line. Now in the x direction for this block, there's not much action, right? There's not much going on in the x direction, but I'm still going to draw it so that I know where the origin is. So there's the x-axis and there's the y-axis. And since I'm drawing these, let's draw the free body diagram or the axes for the second free body diagram. Okay. Not sure why that keeps going away. X and Y. Okay, so I'm going to draw the force that they have in common first, which is that tension. So I've got tension upward here, and a tension upward on the other diagram. And again, what the pulley is doing, the pulley is massless and frictionless. We're not told that, but if we're not given any more information about the pulley, we're just going to assume it's massless and frictionless. Right? It has to be both of those things, because even a frictionless pulley that has mass would take some effort to rotate, and we'd have to consider that, but that's for a future chapter. So all the pulley does is turn that tension around. And I expect box 2 to accelerate downward, right? I expect box 2 to accelerate downward, so the weight of box 2 must be bigger than tension. These are all vectors. And the weight of box 1 must be smaller than that tension in order for box 1 to accelerate upward, right? If there's no slack in this rope, when the 8 kilogram block goes down some distance, the 5 kilogram block has to go up some distance as well, right? So that's going to go up. There's A1. So that means this weight 1 is smaller than that tension. Okay. Generally, when we work a problem with two objects, it opens up the possibility of 4 different equations, right? We can apply Newton's second law in the x and y direction for both objects. In this case, though, the x direction is kind of boring. So I'm still only going to get 2 equations, but it's going to come from 2 different objects. So let's do that. Let's apply Newton's second law to both of these objects. So Newton's second. We'll do this for box 1. And again, it's only the y direction that matters because the x direction is boring. And again, if this is box 1, then this is mass 1 and A1. Okay, and there are only 2 forces here. There's tension upward and weight downward. So that's going to be tension minus M1G equals M1A1. Okay, and for box 2, the sum of the y direction forces is M2A2, and the 2 forces on box 2 are tension upward and weight downward again. So I've got T minus M2G equals M2A2. Okay, so I have 2 equations and 2 unknowns. I don't know tension and I don't know acceleration. But it's actually 3 unknowns, right? Because here's tension. Let's circle those. Here's tension. Here's acceleration. But those are 2 different accelerations. And you might look at this and say, well, didn't you just say when one box goes up, the other box goes down? Yes, I did. And look, I fully expect, again, if the string is not stretching, that when this 8 kilogram block goes down 1.5 meters in some amount of time, the 5 kilogram block is going to go up 1.5 meters in the same amount of time. So the magnitudes of those accelerations will be the same. But do you see that the directions are different? Right? And so that means that their signs may be different. And that all depends on how I drew these free body diagrams. Now look, I called y up as positive for both of these. So that means A1 is positive. We could even write that here. But A2 is against my positive y. So A2 is negative. So if I say A1 equals A2, if I just call both of these circled A's A, I'm going to get the wrong answer. Right? I need that A1, let's say A2 equals minus A1. Right? That's my third equation. And now I have 3 equations and 3 unknowns. All right, that's critical. That's critical. That negative sign is super critical. Okay, so let's make these little boxes go away. All right, so let's solve for A2. So I'm going to replace this A1, oops, not what I meant to do. I'm going to replace this A1 with this expression. All right, so I'm going to replace A1 with minus A2 in that equation. And then I'm going to solve them each for t and set them equal to each other. All right, again, at this point, whatever your favorite method for solving systems of equations is fine. But what we care about is A2. I can solve for A1. It's going to be the same thing, but negative. Or I can solve for that tension, but I don't care what the tension is. I just need A2. So again, my method here will be to solve the two bottom equations for t, and then set the equations equal to each other. So that's m1 a1, and again, a1 is minus a2, so I'm doing a couple steps at the same time. I'm adding the m1g to the other side and setting that equal to m2a2 plus m2g. Okay, that algebra is correct. Thank you. Okay, so what's next? Now I just need to isolate the A2 and solve, right? So I can add, let's do this. I'm going to add this term to both sides. So I'll add that over here. And I'm going to subtract this term to that side. Right, so let's make 1, 2, 3, 4 things go away and do that algebra. Okay, so I'm adding this over. I'm also going to switch them sides. So what does that make it? m1a2 plus m2a2 equals, and I'm subtracting the m2 to the other side, so that's m1g minus m2g. I can factor out the a2, so that's a2 m1 plus m2 equals m1g minus m2g, and now I can divide by m1 plus m2. Let's do that up here. So a2 equals m1g minus m2g divided by m1 plus m2. Great. So what do I notice? That m looks terrible. No, what else do I notice? There's a negative sign upstairs, right? That's m1g minus m2g. Those are those two weights. It's the 5 kilogram weight minus the 8 kilogram weight. That's going to be negative. Oh, good, because A2 should be negative, so that's great. I can plug these numbers in. I'm not going to write the numbers down here. You see them up here, right? So I'm just going to skip to the answer, which is minus 2.26 meters per second squared. I'm going to underline that in purple, because why not? Boom. Great. What do I notice about that? Again, this is not my final answer. But it is negative, as I was expecting, and it's smaller than g. Right? Yeah, because again, this is not free fall. If the 5 kilogram and 8 kilogram, if they were actually exactly the same mass, the system wouldn't accelerate at all. You could give it a shove and it would have a constant velocity, but the system released from rest would do nothing. And if they were just ever so slightly different, the acceleration would be tiny. If the 5 kilogram mass were actually 0, then the acceleration would be g, right? So that's my argument, is I expected a number between 0 and g, and that's exactly what I got. Maybe it's closer to 0 than g because 5 and 8 aren't that different. Okay. Again, that's not the answer. That's the answer to this bit. Find A. Okay, we did that. Now we can find delta t. And it's just a kinematics question like we've done in the past. So let's do that quickly in the free space down here. All right, so let's collect what do we know. We'll say given. We just found acceleration as minus 2.26 meters per second squared. Y initial is 1.5 meters. Y final is the ground, so that's 0. V initial is 0 meters per second. I don't know V final, but I don't care. I should say this is an AY, right? So the equation I'm going to use here is y final equals y initial plus v initial delta t plus half ay delta t squared. Okay, again, we should be careful. This equation we often use for free fall, right? Where ay is actually g, and you put a negative sign in there. This is not free fall, but it is motion in the y direction. Okay, so I can just plug into this. Y final is 0, y initial is 1.5 meters, v initial is 0, so that makes that easy, plus half times minus 2.26 meters per second squared times a delta t squared. Great. So I subtract the 1.5 to the other side, but I also have a negative sign sitting in front of delta t squared. So when I divide that over, that becomes positive, and then I square root that. Right? I trust that you can track that algebra. And what I get for time is 1.152 seconds, which I'll round to 1.2 seconds. Oops. There. 1.2 seconds. And again, my final answer, or my final step of any physics problem is, does this make sense? And I think the answer is yeah. Right? If I drop a box from 1.5 meters, expecting it to take a second or two is reasonable, right? And this takes a little less time than it normally would because it's not accelerating at g, right? Okay, so this procedure is interesting, and there are two things that are interesting about this. One is that it dovetails a dynamics problem to a kinematics question, and two is that it has two objects in the dynamics problem. But again, the procedure is very similar to what we've done before. I'm just drawing twice as many free body diagrams, and it opens up the possibility that you'll have twice as many equations. In this case, we didn't, but in future cases, we may.